Hello, and welcome to the next video in my series on operations management. Now, just a reminder that these videos are geared towards individuals that are relatively new to operations management. So if you are working on your MBA somewhere, these videos are probably a bit below what you would need. However, if you just want a basic understanding of operations management for your schoolwork or your business, then these videos are for you. So that being said, let's go ahead and dive right in. Now, in my last series of videos, I have talked about time series forecasting, where we use past data to try to predict or forecast future data. However, one important thing we did not talk about is how accurate is our forecasted data? How representative is it of data that actually occurs in the future? So in this video, we're going to talk about how to measure the error in our forecasts. So think about this. If the weather person on TV says that the high tomorrow will be 85 degrees, but the high is 88, then the error between the forecast and the actual temperature is 3 degrees. In business and educational applications, it's the exact same way. So if we make a forecast in the future, and then the future happens, say next year, then we can measure the difference between our forecast and the actual data, and that is called forecast error. So we'll be using the same problem we have in the past several videos, and that is where we are working in the Office of Institutional Research for a large Midwestern university here in the U.S. The administration has tasked our office with producing enrollment forecasts for next year based on historical enrollment data. Now the question is, how can we implement forecast error techniques to determine which forecast model, the simple moving average, the weighted moving average, or the exponential moving average, that gives us the most reliable forecast data? So we're going to use our enrollment data, we're going to look at each model, and then determine which model best fits our data. So here is a review of our enrollment data from 2002 through 2011. Now if you notice, I have highlighted the bottom 3 years from 2002 to 2004, and that's because our models will actually go from 2005 to 2011. Now why is that? Well, in this example, we are using a couple of 3-year averages. And as you might guess, it takes 3 years of data to generate our first forecast. So we will need the data from 2002, 2003, and 2004 to generate our first 3-year forecast in 2005. So these models will only span 2005 to 2011 because those will be the years that we have forecast data for all 3 models. Now this is the same enrollment graph we've looked at the past several videos, and I just put a not sign over the years of 2002 through 2004 just to remind you that we're not using those years in our model. We are using those years to generate our first forecast for 2005, but they will not be present in our actual model. Now remember, we have 4 possible, at least at this point, 4 possible techniques to determine our forecasts. We have the naive approach, which is just taking last year's actual data and then moving it to this year's forecast. It's not a very good method, at least for this data, because we do have a trend in our enrollment data. We have the simple moving average, which is merely the average of, in our case, the past 3 years. Each year is weighted the same. So last year is the same as the year before that, which is the same as the year before that. We add those together, divide by 3, and that's our simple moving average for next year. Then we have the weighted moving average. It's similar to the simple moving average, except we place emphasis on the most recent year. So you've probably been in a class at some point where the teacher assigns weights to certain assignments. Maybe your midterm, your exam, your research paper have a greater weight on your final grade than other things. The weighted moving average works the exact same way. So last period may have a higher weight than the period before that, and then the period before that. And finally, we have the exponential moving average, which, by using a smoothing constant, one number in the formula, we can emphasize data that's more recent, or we can spread the emphasis out further back in time to include more years in the past. Remember, it's a value between 0 and 1, and most applications, at least in business and education, call for a value between 0, 0.5 or 0.1 and 0.5. So in my previous video, I go over all these in much greater depth. So if you want to review these, please take a look at my last video. So here is a comparison of our enrollment in green and then our 3 moving average techniques in the blue, red, and yellow. So if you just take a cursory look at this, which method seems to be closer to our actual enrollment? Well, if you're looking at the same graph I am, it's the blue, which is the 3-year weighted moving average. So let's take a look at each one of these individually. So here we have the 3-year simple moving average alongside our enrollment. Now it's hard to tell exactly how this relates to the others, but we'll flip back and forth so you can see. Now in this graph we have the 3-year weighted moving average with our enrollment. Well, let's flip back and forth a couple of times to the simple moving average. So what do you see? Well, you should see that the weighted moving average is actually physically closer to the enrollment. And another way to think about error is the distance between our actual data, in this case enrollment, and our forecast, which is in the blue. So if that distance between the two, the narrower it is, the less error that is present. So here's the graph for our exponential moving average with an alpha of 0.5. Now I'll flip back and forth between all 3 so you can see how they relate to each other. Alright, so we're back to our composite graph, and again you can see how the 3-year weighted seems to be closer to the enrollment. However, looks can be deceiving. If I cover the left-hand side of this graph, well then the 3-year weighted in the blue does look like it's closer to the enrollment than the other 2. But if I cover the right half and then show you the left half, now what do you think? Here it's a lot harder to tell, isn't it? It's really hard to tell which one is closer to our green line, our green enrollment, over this time period. So you have to be careful in making assumptions about segments of your data. You have to look at the whole thing in total. So what is forecast error? Just remember that it compares our forecasted data with the actual data for any given period. So if we forecast 30,000 students for the fall of 2012, but 30,500 actually enroll, well, our forecast is 500 students off. We under-forecasted by 500 students. So it's merely the difference between the actual and the forecasted. The error helps us determine the accuracy of different forecasting models. So remember, in this case, we're looking at 3 models: simple moving average, weighted moving average, and exponential. And we can find the accuracy over the long run of each model. Now, luckily, using these techniques only requires very simple mathematics to do the calculations. Nothing beyond the 4 basic operations of adding, subtracting, dividing, and multiplying. Now our goal is to find the lowest possible error among these several alternatives. So we're going to check the error of the SMA, we're going to check the error of the WMA, we're going to check the error of the EMA, and then we're going to figure out which model produces the lowest possible error. Now the general formula for the forecast error is very simple. It's just the actual data minus our forecasted. So using our weather example from before, if tomorrow's high is actually 88 degrees, but the Weather Channel said it was going to be 85, our forecast error is 3 degrees. Now, if we have a negative error, that means we over forecasted. So if we have a forecasted temperature tomorrow of 90 degrees, but it's only 86, then we're going to have a negative error, which means we over forecasted, we overshot what the actual data was by 4 degrees. While a positive error implies that we under forecasted. So if the forecasted temperature tomorrow is 85 degrees, but it gets up to a high of 92, then our actual data is 92, our forecasted was 85, so we're going to have a positive forecast error of 7 degrees, and we under forecasted what the temperature was going to be. So what we're really asking here is, how far off are our forecasts from the actual data for any given period? When we graph our forecasted alongside our actual data, how close are they? Now, to do this, we're going to use 3 simple error techniques, or 3 error measurements. The first one is called the mean absolute deviation, or MAD. And this formula may look complex to you, but it's actually extremely simple. We're going to take the actual data value, subtract what we forecasted, and then we're going to find the absolute value of that. That's what the 2 vertical lines mean on either side of actual minus forecast. So remember from math in grade school that the absolute value is simply the magnitude, or even simpler, the positive part of any number. Regardless of whether the actual and the forecast is positive or negative, since we take the absolute value, it's going to be positive. Now, the sigma on the left-hand side simply means add all those up. It means summation. So we're going to take the actual minus the forecasted, find the absolute value for each year, and then add up all the years. Then we're going to divide by the number of years we have in our model, which in this case is 7 years. And that's it. Each forecast value will be a certain distance from the actual value. And we're going to find the average of those distances. Our next method is called the mean squared error. And this is similar to the MAD, but we're going to take our actual minus our forecast for each year, and then we're going to square it. And then we're going to add all those together and then divide by our number of years, which is 7. Now, what does this do? The MSE helps exaggerate differences. So when we square our error term there in the middle, we're going to actually exaggerate the distance from our actual enrollment. We're going to exaggerate that. So it helps us sort of tease apart the error term in our measurements. And finally, we have the mean absolute percentage error. Now, the easy way to think about this is, well, what percentage are we off from our actual data? So our forecast may be 2% away from our actual data, or 5% from our actual data. It's just a percentage. And even though that formula looks very complex down there, it's actually very simple. Again, we're just taking our actual minus our forecast, taking the absolute value of that, and then dividing it by the actual data. So it's just the same way you'd figure out any other percentage. Now the 100 next to that just means that we're going to multiply it by 100 to get an actual percentage. Now we're going to add all those up. We have our sigma sign there. We're going to add all those up for each year, then divide by our total number of years, and then we will get the average percentage distance, or average percentage error over those 7 years. Now we're going to work an example of each one. So if they're not quite clear right now, once we do the examples, they should be crystal clear. So here are the values we're going to try to find in this example. Now we have 3 models on the left-hand side: our 3-year simple moving average, our 3-year weighted, and our exponential moving average with an alpha of 0.50. And of course, we have 3 techniques. We have the MAD, the MSE, and the MAPE, or the MAPE. So this means we have to calculate 9 different values. Now, am I going to sit here and make you watch me calculate 9 different values? No. So we're going to do one example of each, and then I will assume you can go back and do the rest for yourselves. So let's go ahead and do the MAD, or the MAD, for the 3-year simple moving average. Now we have our enrollment column, we have our 3-year SMA forecast for each year. So remember, to find the MAD, we take the enrollment minus the forecast, and then take the absolute value. That's it. So we do that for each year. We add up all those years, the error terms there on the right-hand column. We add all that up, and we get 1,861, and then we divide by 7, which is our number of years. So we come up with a MAD of 266. So exactly what does this mean here? Well, it means on average, our forecasts were 266 students away from our actual enrollment. So I went ahead and did the MAD for all 3 models. So we just did the 3-year simple, which is 266. The 3-year weighted moving average, the MAD was 200. And the exponential moving average of alpha of 0.5 was 233. So you can see that at least for the MAD, it's the 3-year weighted that produces the smallest error. So let's do the MSE, and this time we'll use the 3-year weighted moving average. So we have our enrollment and our 3-year weighted forecast, and to find our MSE, we just take the enrollment minus the forecast and then square it. So then we get our error terms over on the right-hand side. Once we have our error terms for each year, we just add them up, divide by 7, and we have an MSE of 60,509 for the 3-year weighted moving average. So again, I went ahead and calculated the MSE for the other 2 models. So our 3-year simple was 94,234 for our MSE. The 3-year WMA was 60,509. And for the exponential moving average, it was 75,907. So again, the 3-year weighted moving average has the lowest MSE. So now we're going to do the MAPE, or the MAPE, which is the mean absolute percentage error, which is a fancy way of saying what percentage is our forecast off of our actual enrollment. So we have our enrollment column and our forecast column, and to find that percentage, we just take the enrollment minus the forecast, find the absolute value of that, and then divide by the enrollment. And then we get what percentage our forecast was off. So those are our error terms and percentages over on the right-hand side. We add all those percentages up, and then we divide by 7, which is our number of years, and we get 0.77%. So on average, our forecast was 0.77% off of our actual enrollment. So again, I went ahead and did all the MAPEs for each model. So for the 3-year simple moving average, we had a MAPE of 0.88%. For the 3-year weighted moving average, we had a MAPE of 0.66%. And for the exponential moving average, with an alpha of 0.5, we had a MAPE of 0.77%. So now we can answer the question, which forecasting method produces the least amount of forecast error? Well, if we look at our chart, for this data, and for these 3 methods, the 3-year weighted moving average is the most accurate. It has the lowest MAD, it has the lowest MSE, and it has the lowest MAPE. So based on this data and these 3 methods, and you have to keep that in mind, this is only for this data and these 3 methods. You cannot extrapolate this out into something else. You have to stick with what you have. So according to what we have, the 3-year weighted is the best model for predicting future enrollment. So again, if we look at our composite chart, this should make sense. The 3-year weighted moving average is the closest to the actual enrollment in actually raw distance. Now on the left-hand side of our graph, it's really hard to tell. And in the next video, I have a little surprise for you. We're going to be looking at a very complex set of data that has around 57 data points. And it's really hard to tell by looking at it which method is going to produce the best model. Over on the left-hand side, it's really hard to figure out. But on the right-hand side, it's pretty obvious. The 3-year weighted in the blue is definitely the closest to our enrollment. Now the next closest seems to be the exponential in the red. So if we go back to our chart, we can see that the EMA at the bottom there has the second lowest error of all three. And that makes sense with our graph. It's kind of in between the blue and the yellow. Now, with respect to the yellow, that's the simple moving average. And that appears to be the furthest away from our actual enrollment. And if we go back to our chart, that is the case. It has the most error of all three models using all three error methods. So what can we make of all this? How should we interpret our findings? Now, why is the 3-year weighted moving average the model that produces the least amount of forecast error for this data? Well, if you remember what I said earlier and in previous videos, this enrollment data has a very strong trend upward. The enrollment has had a strong trend upward over these years. So, since the weighted moving average only focuses on the past 3 years and nothing before that, it really emphasizes that trending data. It really sort of captures it. Now, it also has weights that are favorable for capturing recent data. If you remember, we gave the most recent year a weight of 4, the year before that a weight of 2, and the year before that a weight of 1. So that's a total weight of 7. If you calculate the decimal weights of those fractions, you have 0.57, 0.29, and 0.14. So you can see the year before, the first year we're using for our 3-year weighted moving average is given a weight of 0.57. That's a tremendous amount of weight. And then before that, 0.29 and 0.14, of course. Now, remember, the simple moving average weighs the previous 3 years equally. So they're each 1/3. So it's not going to pick up a trend nearly as easily as the weighted moving average will, because of the extreme amount of weight given to previous years in the weighted. Now, the EMA is also a weighted moving average, but it's just not as strong as the regular weighted moving average. So by contrast, the weights of the previous 3 years using the EMA are 0.5, 0.25, and 0.125. We're essentially having it each time. And that's just over the previous 3 years. But because of the nature of the EMA, the weights for the EMA never ever reach 0. They keep getting smaller and smaller and smaller and smaller and smaller. Very, 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 very tiny weights to infinity, actually. So whereas the WMA stops dead cold after 3 years in the past, the EMA keeps inputting previous years into the very distant past, even though it's at a very, 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 very small amount as you go back, but nonetheless it's still there. Therefore, the weighted moving average for the 3 years, here in our case, really picks up the trend much better. Now, the best model would be one that takes into account or sort of corrects for trends in data. Now, of course, will we be doing a video about that? Probably. All right, so that is our video for how to measure our forecast error. Now, I want to remind you and stress a couple of things. When you find the forecast error, it's only applicable to the data you have and the models you're using. Now, in our chart, it was fairly obvious because the weighted moving average had the lowest error across all 3 measurements. Now, you may have a scenario where the weighted moving average has the lowest error on the MAD, but then maybe another method has a lower error on the MSE. So then you'll have to sort of determine, using your judgment, on which model actually produces the least amount of error. It's not always clear cut. So just keep your mind on the data you have, the models you have, and then you use your judgment to figure out what model produces the least amount of error. All right, so that wraps up this video. Again, thank you very much for watching, and I look forward to seeing you again next time.